Chapter 4, Descriptive Statistics. Section 4.1, Descriptive versus Inferential Statistics. It is a source of mild but endless frustration to me that the word statistics is overloaded. It signifies different things in different contexts. Margin note. Overloading is a term in programming when the same symbol has different operations depending on its context. For example, the plus sign can mean mathematical addition or string concatenation. Back to the text. Let me delineate two distinctions of the word statistics. First, descriptive statistics. These are numbers that characterize a data set. You will learn many descriptives in this chapter, and you may already be familiar with terms such as mean, median, variance, skew, spectrum, and covariance. Second, inferential statistics. These are algorithms that are applied to one or multiple sample datasets in order to test whether the descriptive statistics of that dataset are likely to generalize to other datasets. You will learn inferential statistics throughout the rest of this book, though not in this chapter. And you may already be familiar with terms such as f-value, t-value, ANOVA, and regression. Why is this an important distinction? With descriptive statistics, we do not care about the relationship between the sample data and the population from which those samples were drawn, nor do we care about generalizing from one sample to other samples or other populations. We do not attempt to compare the characteristics of one dataset with the characteristics of another dataset. Instead, the purpose of descriptive statistics is simply to obtain numeric representations of one particular dataset. Inferential statistics, in contrast, is all about using a particular dataset to understand the characteristics of the population from which that sample was measured. In other words, inferential statistics is about using data that we have to make claims about data that we don't have. An example. Let's say we measure the heights of a group of men and a group of women. We find that the average heights are 178 centimeters and 171 centimeters for the groups of men and women, respectively. Those are the descriptive statistics of the two groups, and in these two groups, men are, on average, exactly 7 centimeters taller than women. There is no uncertainty and there are no probabilities, but can we infer that men are 7 centimeters taller than women in general? That is, at the population level, including men and women that we did not measure in our sample. That is not a question that descriptive statistics can answer. We would need to use inferential statistics, and the answer will depend on factors including how the samples were collected, sample sizes, and the variances within each group. I hope the distinction is clear. This chapter is entirely focused on descriptive statistics, as are the next several chapters. You will begin learning about inferential statistics in Chapter 8. Because most people associate the word statistics with inferential statistics, I will include the qualifier descriptive when referring to descriptive statistics and simply write statistics when referring to inferential statistics. Section 4.2, Data Distributions. Let's start by thinking about an experiment. Let's say I approach 300 people and ask each person the same question. How many times have you watched the Gangnam Style video on YouTube? Before reading the next paragraph, I would like you to think about the category of data type of our experiment. See table 2.8, page 40. I do not know the timestamp, so best to have the book in front of you and refer back to page 40. Two observations about these data. First, videos are not limited to integers. You can stop in the middle of a video and report that you have watched 0.5 Gangnam Style videos. Second, 0 is a meaningful number. Watching that video 0 times literally means the absence of having watched that video. And this also means that watching the video 10 times is twice watching it 5 times. And it is not possible to watch the video -2 times. Thus, these data are of type ratio. Back to data distributions. How would you visualize these data? You could simply visualize the data table that contains 2 columns, person ID in one column and number of times watched in the other column, and 1 row per respondent. This is illustrated in figure 4.1. Figure 4.1 simply shows 5 rows of a data table where the left column is the respondent ID and the right column is the number of times watched. So we have respondent ID is integers 1 through 5, and times watched is 3, 0, 14.5, 13, and 6. So these are just 5 rows of a fake data set that describes the number of times that different people have watched a particular YouTube video. Back to the text. But this is not a great visualization, nor is it scalable to large data sets. Another possibility is to create a graph with the person surveyed on the x-axis and the number of times watched on the y-axis. This is illustrated in figure 4.2a. Now, this is better than a table of numbers, but is that really the best way to visualize the data? The ordering on the x-axis is meaningless in that we do not expect neighboring data samples to have anything to do with each other, assuming that we sampled randomly from the population. Figure 4.2 has 2 panels, panel A and panel B. Panel A shows the scatter plot that I was just referring to. So each dot corresponds to a respondent index on the x-axis, and the y-axis encodes the number of times watched. There is 1 small black square for each of the respondents, and it appears that most of the data are clustered at relatively small numerical values, close to 0, and there are fewer and fewer data values as we get higher, up to around 35 or so. I will describe panel B of this figure in a few moments. Back to the text. You're probably already thinking that a histogram is a better way to visualize these data. I agree. Figure 4.2b shows the histogram of these data. As I wrote in the previous chapter, a histogram is a lossy visualization, meaning that we lose some information. However, what we may have lost is more than compensated for by what we gain in understanding the distributional characteristics of the data. The most prominent characteristic of this distribution is its slope downwards. This is not a Gaussian or even a symmetric distribution. Most of these surveyed people watched the YouTube video a small number of times, and the counts decrease steadily. But that decrease is not purely monotonic. Figure 4.2b shows that there is a small increase in the counts around the number 18. So more people have watched that video around 18 times compared to the surrounding bins. Whether that bump in the histogram would be reproduced in a different sample is a separate question. The important point for now is that this feature of the data is not apparent when looking at the raw data, either in a data table or in a scatter plot. On the other hand, the scatter plot in panel A shows 1 large value at around 35 times watched, which might be an outlier. Now, that data point is technically present in the histogram, but its bar has a y-axis height of 1, making it difficult to see without close inspection. Indeed, you might have missed it until I just pointed it out right now. The point here is that there is no single way to visualize data. Some visualizations are better than others to understand certain characteristics of the data. Even in simple data sets, inspecting multiple visualizations will help you understand and appreciate the data. These qualitative observations reveal characteristics about the data that would be difficult or impossible to discern from looking at the table of numbers. Later on in this chapter, you will learn how to quantify these qualitative observations, but the important concepts here are: 1, we visualize the data in 2 ways. a scatter plot, and a histogram, and each visualization revealed some different characteristic of the data. And 2, we remarked on the shape of the histogram, which provides qualitative information about the distribution of the data. Because we are focusing on the distribution, it doesn't matter if we plot the data in counts or convert into proportion. Such a transformation does not alter the shape of the distribution, nor does it affect the descriptive statistical properties of the data that you'll learn about later in this chapter. Section 4.2.1, Empirical versus Analytical Distributions. Distributions come from one of two sources: measured data or a mathematical formula. These are also called empirical and analytical distributions. An empirical distribution creates a histogram like what you saw in figure 4.2b. It's called an empirical distribution because it is made from empirical data, that is, data that are measured from the world. Although in this case, these are fake data, but they simulate real-world data. Furthermore, each dataset will have a different empirical distribution even if the samples are taken from the same population. That is, if our experiment involves drawing samples at random, then each new dataset will have a different histogram, although, of course, we would expect the overall shape of the distribution to be the same. Figure 4.3 illustrates this concept. To create the two histograms, I sampled random numbers using the computer's random number generator. The exact histograms are not the same because of random sampling, but I'm sure you agree, and if you look at the figure, you'll definitely agree with me, that the overall qualitative features of the distributions are the same. So figure 4.3 has two panels, panel A and panel B. Panel A is labeled sample A, panel B is labeled sample B. Both panels show histograms of random numbers that are drawn from a normal distribution with the mean of approximately 36. Now, the bars in the two histograms are not exactly identical. They have different heights, but they overall look basically the same. They look like a slightly noisy Gaussian or bell curve distribution. Back to the text. I explained in the previous chapter that although histograms should be visualized using bars because they are created by binning the data, lines can be used when the binning resolution is reasonably high and the lines will facilitate comprehension. You can imagine that as the sample size grows larger and larger towards an infinite amount of data, and the binning gets smaller and smaller towards an infinitesimal width, then there really is no difference between bars and lines. Margin note: analytical distributions are also called theoretical distributions, not because they are theoretical in the sense of not existing, but because they are derived from mathematical theories. End margin note. This brings us to analytical distributions. An analytical distribution is not created by binning measured data, but instead by evaluating a mathematical formula. Consider, for example, equation 4.1. Equation 4.1 reads f of x equals the quantity 1 over sigma times the square root of 2 pi times e to the power of the quantity minus x squared over 2 times sigma squared. That equation is called the Gaussian or the normal function. Now, don't worry for now about what it means, where it comes from, what the parameter sigma represents. You'll learn a lot more about the Gaussian formula throughout the book. The point for now is that it is a mathematical formula that is a function of variable x. It's not computed from empirical data, and we can evaluate the formula to create a graph, like figure 4.4. Figure 4.4 shows a Gaussian probability density. It is a smooth, curvy line that looks like a bell curve. It is a Gaussian bell curve normal function. Back to the text. The y-axis of analytical distributions can be normalized to different values, which can lead to different interpretations. In many cases, the distributions are normalized to probability such that the sum over all the values of the distribution is 1. For a continuous distribution, this is the integral from minus infinity to plus infinity. But what does that mean? It means that an analytical distribution tells us about the probability that certain ranges of numerical values will be observed. For example, in the Gaussian distribution, numbers closer to x equals 0 are more likely to occur than numbers further away from 0. There are myriad analytical distributions in statistics. You will see several examples later in this chapter, and you will learn perhaps a half dozen throughout the rest of this book. Section 4.2.2, the uses of data distributions. Data distributions have several applications, including, number 1, they provide a visual and qualitative overview of the characteristics of the data. Number 2, most statistical procedures are based on assumptions about the distributions underlying the populations from which these samples were drawn. Therefore, understanding distributions will help you determine which statistical procedures are appropriate for which data sets. Number 3, statistical inference, that is, determining the probability that a sample statistic occurred by chance, is based on comparing an observed statistical value against a distribution of statistical values that are expected if the finding really were due to chance. Margin note: sample statistic refers to descriptive statistics of a sample. They are occasionally called sample parameters, although the term parameters is more commonly used to describe population characteristics. Number 4, computational simulations in biology, physics, and computing are often based on sampling from distributions. For example, generative artificial intelligence models that create music and text and faces involve randomly sampling certain distributions. 5th, in statistical modeling, the distribution of residuals, that is, the differences between observed data values and model predicted data values, is inspected to evaluate the quality of the model. 6th, assumptions about distributions underlie statistical laws such as the law of large numbers and the central limit theorem. Thus, understanding distributions will help you understand fundamental statistics concepts. Section 4.2.3, examples of distributions. You will learn about various distributions later in the book, but I'd like to give you a sense of what some analytical distributions look like. Figure 4.5 shows 4 distributions and some of their parameters. Please don't worry about what the different distributions mean, where they come from, how they're used, or what the term DF stands for. I promise that this will become clear to you later in the book. For now, focus on the qualitative features of the distributions. Figure 4.5 shows 4 example analytical distributions. There are 4 panels. The top left, panel A, is a Gaussian or bell curve. This looks like a canonical Gaussian or bell curve function, so it starts close to 0. It smoothly goes up, starts at y equals 0, at x equals around -4, and it smoothly increases up until x equals 0, and then it smoothly decreases as x gets into positive numbers. Panel B shows a t-distribution with df equals 20. This looks a lot like a Gaussian distribution. In fact, it's almost the same thing as a Gaussian. I will get into the distinction between a t-distribution and a Gaussian distribution in a later chapter. Panel C shows an F distribution. It is undefined for negative values, so the graph starts at 0, and it rises very, very quickly up to a peak, and then it falls more gradually down to lower numbers as x increases to a value of 10, which is the maximum shown on this graph. And finally, panel D shows a chi-square distribution, and it looks a little bit similar to an F distribution in the sense that it is defined for positive values only on the x-axis. It increases very, very quickly up to a peak at around 1, and then it falls gradually down to smaller and smaller numbers on the y-axis as the x-axis increases. Back to the text. I will make some general remarks in the paragraph below the figure, but before reading that, I would like you to make some observations based on what you see in the figure. So here are my qualitative observations. Some distributions can be defined for negative and positive numbers, others only for positive numbers. Most distributions taper to 0 on one or both sides of one bump. Some distributions are symmetric, while others taper to 0 faster on one side of the bump. Some parameter values have a relatively small impact on the distribution, while other parameter values can cause qualitative changes to the shape of the distribution. Now for some empirical distributions. Empirical distributions can be more varied than analytical distributions because they are based on measured data, and there might be limited sample sizes or equipment issues that create unusual looking distributions. The data in figure 4.6 were generated from random numbers, but they contain characteristics that you might see in real data. As in the analytical distribution examples, I would like you to make some qualitative observations of the histograms before reading my observations. Footnote. Learning is an active process, and I am trying to encourage you to take an active role while reading. This is admittedly slightly more difficult to do while listening, so I hope you are looking at the text along with listening to my voice. Figure 4.6 shows 4 examples of empirical distributions. These are 4 histograms. The top left histogram in panel A shows a triangular looking distribution where the values seem to increase roughly linearly up to a peak and then decrease roughly linearly. Panel B shows a uniform distribution, so the bars are roughly equal heights all throughout the x-axis with some noise notwithstanding. Panel C shows a distribution that has one bar approximately halfway up the y-axis all the way to the left, and the next bar is a peak, and then the bars just keep decreasing from there, except all the way in the very right, the last bar on the right is considerably higher than about half of the other bars in the distribution. Finally, we have panel D, which shows a distribution that looks like 2 Gaussians that are mixed together. There is one Gaussian towards the right that has a large peak, and it looks like there's another shoulder of a Gaussian, a smaller peaked Gaussian, to the left of that larger Gaussian. Back to the text. Here are my remarks. Panel A, this is the top left one. This one looks a little bit like a distribution, but decreases linearly instead of non-linearly, and it doesn't go down to 0. The rate at which a distribution falls to 0 is called kurtosis, and you'll learn how to quantify and interpret kurtosis later in this chapter. Panel B, this is the top right panel. This shows data drawn from a uniform distribution, meaning that any value between the lower and upper bounds, here 0 and 1, is equally likely to occur. Now, it looks like some values are more likely than other values, but this is an illusion caused by sampling variability. Panel C. This is the lower left panel. This shows a power law distribution where the number of occurrences is inversely related to the size of those occurrences. Power law distributions are taken as evidence of scale-free organization. Lots of interesting physical and biological systems have distributions with this shape, ranging from earthquake magnitudes to brain activity patterns. The small bump on the right tail of the distribution is my attempt to simulate an equipment problem whereby large data values are clipped and take on a maximum value. This is an artifact in the data that would need to be addressed, and the researcher would need domain knowledge about the system and the equipment to determine whether and how to deal with this artifact. Panel D. This is the lower right panel. Some distributions have multiple peaks, indicating several clusters of high probability data values. This example is called bimodal because there are two peaks. More generally, such distributions are called multimodal. A distribution with one peak is called unimodal. Section 4.2.4, Quantifying Qualitative Characteristics. One more example of distributions to segue to the rest of the chapter. Consider the three analytical distributions in Figure 4.7. Make some observations about how they differ and how they are the same. Figure 4.7 shows three Gaussian distributions that illustrate two features of distributions. The distributions were height normalized to facilitate interpretation. So we see distribution 1, 2, and 3. Distributions 1 and 2 both have their peak, their maximum value at x equals 0, but distribution 1 is wider, it is fatter than distribution 2, which is narrower. Distribution 3 has the same fatness as distribution 1, but its peak is shifted to the left. Back to the text. First of all, notice that the three distributions have roughly the same shape in that they are all symmetric around their single peak and tapered to 0 on both sides. In fact, they are all Gaussian distributions. Two distributions peak at the same x-axis location, while the third is shifted to the left. Of the two distributions with the same peak location, one is wider or fatter than the other. These are qualitative observations about the central tendency and the dispersion of the distributions. Qualitative inspection is important, but we need to quantify these characteristics by assigning numerical values to these observations. Section 4.3, Central Tendency. Central tendency is an umbrella term that generally refers to the typical or most likely value of a dataset. Central tendency is one of the most important descriptive statistics and is often used in inferential statistics. Indeed, many datasets are described using only their central tendency. There are several ways to quantify the central tendency of a dataset, depending on the type of data and the characteristics of the data distribution. Wikipedia lists 18 measures of central tendency, and the three most common are the mean, the median, and the mode. The mean, also known as arithmetic mean or average, takes up most of the space in the sections below because it is the most important and most widely used. Section 4.3.1, Mean. To compute the mean, sum all the data values and then divide by the number of data values. Here's the formula. Formula or equation 4.2 has x with a line over the top. This is typically called x bar. On the left equals n to the power of minus 1 times the sum from I equals 1 up to n of x sub I. Let me spend a paragraph on the math notation to make sure that you understand that formula. The x is a placeholder for the variable under consideration, and the horizontal bar on top is the typical notation for the average of x. In formal statistical notation, mu or mu sub x, the mu is a Greek character. It looks a bit like a U, but the left side has a longer vertical drop. So mu or mu x indicates the population mean, while x bar indicates the sample mean. In other contexts, you might see mu for the average of a set of numbers, regardless of whether those numbers are from a sample or a population. N is the sample size, so n to the power of minus 1 is the same thing as 1 over n, i.e. dividing by the sample size. The capital sigma, so is the Greek character sigma, is a summation sign indicating that you sum all of the values in variable x. Let's work through an example. Compute the average of the following dataset. Here, equation 4.3 has x equals the set of integers minus 2, 0, 4, 1, 7. The average is x bar equals 2. Summing over all the values gives 10, and dividing by 5, which is the number of numbers, gives 2. The mean can be visualized as a vertical line in a histogram, as in figure 4.9. Figure 4.9 shows a histogram of a data set that has a symmetric unimodal distribution. It's not quite a Gaussian because it's a little bit too narrow for a Gaussian, but it is roughly symmetric. And there is a vertical, thick dashed line around the center of the distribution indicating the mean. Back to the text. The mean can be computed for any numerical dataset, but it is not necessarily easily interpretable for all datasets. The mean is a useful description of a dataset only when the data distribution is, number 1, roughly symmetric, and number 2, unimodal. Why is this the case? Come up with your own answer based on figure 4.10 before listening to my answer below. Figure 4.10 has 2 panels, panel A on the left and panel B on the right. The title of panel A is Non-Symmetric Distribution. We see a histogram that depicts a power law-like distribution, so lower values have a higher count, and the larger the value on the x-axis, the smaller the value on the y-axis. The mean is indicated by a thick vertical dashed line, and it is somewhere around 20% of the way from left to right. Panel B is titled Bimodal Distribution. Here we see 2 peaks, looks like 2 Gaussian distributions that are put together, and the mean, again indicated as a vertical dashed line, is right in the middle, like in the valley between the 2 peaks. The figure caption reads, Failure Scenarios of Interpreting the Arithmetic Mean. Note that these are not failures of the math or of the data. For example, dividing by 0 would be a failure of the algorithm. These are data distribution shapes that impede a straightforward interpretation of the mean. Back to the text. Let's start with the left panel of figure 4.10. This distribution follows a power law where increasing values have decreasing probability. The problem is that the mean value does not reflect a central tendency in the data. In other words, the mean is not representative of typical values. Distributions with this shape are sometimes called scale-free because they have no characteristic scale or numerical value. Now consider panel B. The data are bimodally distributed, and the symmetry puts the mean value right in the middle of the 2 peaks. So how can we justify calling the mean the central tendency of the data when almost none of the data values is close to the mean? There are myriad other specific examples of where the mean value is and is not representative of the most commonly observed data values. The conclusion from these examples is that although the mean is a simple algorithm and can be computed for any numerical dataset, it is easily interpretable as the central tendency of the data only when the data distribution is unimodal and roughly symmetric. A few other notes about the mean. First, the mean value does not necessarily appear in the data. Consider the average of the numbers 1, 3, and 4. This is different from the median and the mode, as you will soon learn. Second, the mean is suitable for interval or ratio data. It is possible to compute the mean of other data types in some cases. An example is product ratings, as I mentioned in the previous chapter. The interpretation can be weird though. For example, the average number of children born to a family in the USA is 1.9. So is the second child missing 10% of their body? Averaging nominal data almost never makes sense. If you numerically label chocolate ice cream as 1, vanilla ice cream as 2, and strawberry ice cream as 3, then computing the average implies that chocolate plus vanilla equals strawberry. Just doesn't make sense. Third, the mean is not the same thing as the expected value, although those 2 quantities can be equivalent under certain assumptions. If you are not familiar with expected value, then don't worry about it for now. I will explain this in Chapter 8, and I mention it here only to preemptively avoid confusion. Fourth, the mean is sensitive to data observations with extreme values, such as outliers. The smaller the sample size, the more problematic this becomes. You'll get to explore this in exercise 6. Fifth, even if the data distribution is roughly symmetric and unimodal, the mean is more informative about the central tendency when the variance of the distribution is smaller. This leads to a descriptive statistic such as the coefficient of variation. More on this point later. Section 4.3.2, median. The median is the data value that cuts the data set into two equal-sized pieces. Imagine sorting the data from the most negative value to the most positive value. Then the median is the data value exactly in the middle. In other words, 50% of the data are smaller than the median, and 50% of the data are larger than the median. There is no widely agreed upon notation for the median. Sometimes people use MED parenthesis X, where the MED would be in italics, but the most common formulation is simply to write out the median of the data. Here's the formula for the median in equation 4.4. The median of the data X equals the ith index in X, so the ith element in the sorted data values of X, which here I'm indicating using a tilde character on top of the X. Tilde character is that like squiggly horizontal line that you see in Spanish language. So X tilde sub I, so index I, where I equals the quantity n plus 1 divided by 2. Back to the text. X tilde indicates the sorted data, and I is the index corresponding to the middle value. And I'll get back to the plus 1 part in a bit. Let's try with a simple example. Determine the median of the following data set. Now you can figure out the answer just by looking at the numbers, but make sure you understand how your intuition is confirmed by equation 4.4. Remember, that was the sorted data, and then it's the ith element of the sorted data where I equals n plus 1 over 2. So here's the data set. X equals 0, 4, 1, minus 2, 7. To compute the median, sort the values and take the one in the middle. So X tilde equals minus 2, 0, 1, 4, 7. The value in the middle is 1, which I've bolded. In this data set, n equals 5, and so index I in equation 4.4 is 5 plus 1 divided by 2 equals 3. So the 3 indicates that the third data value in the sorted data set is the median. There are two numbers smaller and two numbers larger than the median. By the way, the mean of this data set is 2. That value does not appear in the data. Now compute the median of this data set. Y equals 10, 0, 4, 1, minus 2, 7. This one is a little bit trickier. Here's the sorted data set. Y tilde equals minus 2, 0, 1, 4, 7, 10. There is no single value, there's no one value that cuts the data in half because there is an even number of data samples. So what do? Does this data set have two medians or no median? The answer is that the median is 2.5. This comes from the average of 1 and 4, which are the two numbers in the middle. Now, the number 2.5 does not appear in the data, but this value evenly splits the data into two halves, so it is consistent with the purpose of the median. On the other hand, an infinite number of values will evenly split the data, like 1.000001, or pi, or 3.99999. Defining the median as the average of the two middle numbers guarantees that the median is unique for a given data set. The conclusion here is that when a data set has an odd number of elements, the median is the exact center value, the middle of the sorted data values. And when a data set has an even number of elements, the median is the average of the two center values. Figure 4.11 shows an example distribution in which the median and the mean are nearly the same. Indeed, the mean and the median are identical, or at least very close to each other, in symmetric distributions. Figure 4.11 shows a similar histogram as what I described earlier, but here it has the mean in a thick black dashed line and the median drawn as a thick gray dotted line. And visually, they appear to overlap basically perfectly. The figure caption reads, "The mean and median are very similar for symmetric distributions." Back to the text. Is the median always appropriate and easily interpretable for any numerical dataset? Let's revisit for figure 4.10, but plot the median in addition to the mean. Please take a moment to inspect figure 4.12 and draw some conclusions about the median before reading my comments below. Figure 4.12 shows the same two distributions that I described earlier in figure 10, but additionally showing the median. So again, we have two panels, the left and the right. Both panels show histograms of data with the mean and the median drawn on top. The left panel shows the power law distribution, where values all the way to the left of the distribution are more likely to be observed, and the probability of observing values, or the count of observed values within each histogram bin, decreases with increasing values on the x-axis. We see the mean and the median are both drawn in. The mean is slightly higher, so slightly more to the right than the median. Panel B shows the bimodal distribution, looks like two Gaussians. Here, the mean and the median are both in the valley between the two peaks, and they are not identical, but they do appear to be very similar to each other. Back to the text. The left panel highlights a subtle but important distinction between interpretations of the mean and median. Now, you learned above that the mean is not representative of the typical values in this particular data set. The median, on the other hand, does exactly what it's supposed to do. It cuts the data set into two equal-sized bins. Still, this figure shows a difficulty in interpreting the median because people generally think of the median as indicating the central tendency of a distribution, and so without showing the distribution, people are likely to imagine that the median value is the most typical value. Same story for the right side panel. The median cuts the data into two halves, but it does not reflect a typical value any more than the mean does. Footnote: I created this bimodal distribution to illustrate an important concept about descriptive statistics, but a real-world distribution like this is probably composed of two qualitatively different samples, for example, heights of children and adults. If you see a distribution like this, a bimodal distribution, in your data, you should investigate whether it is possible to separate the data into more homogeneous subsets. End footnote. There are several other important features of the mean and median to know about, especially as they relate to sample size and outliers. You will have the opportunity to explore these concepts in exercise 6. Section 4.3.3, Mode. Let me start with a side note about terminology. The mode, as a measure of central tendency, is not the same as the number of peaks in a distribution, which are described using terms like unimodal, bimodal, and multimodal. It's a point of potential confusion to be mindful of. Anyway, the mode of a dataset is the most common value. To obtain the mode, you simply count the number of unique observations and take the data value with the most number of observations. That's called the modal value. The mode is most suitable for categorical data. In fact, it is the only measure of central tendency that is appropriate for nominal data like movie genre or ice cream flavor. The mode can be computed for numerical data if those data are discrete, so integers or bins, although in these cases the mean is usually more appropriate. Indeed, with arbitrary precision data, it is unlikely that any one data value will be repeated. For example, imagine measuring the weight of penguins using a scale with microgram precision. A microgram is 1/1,000,000th of a gram. It is just mind-bogglingly unlikely that two penguins will have exactly the same weight at that precision. Here's an example. Compute the mode of the following integer dataset: 10, 0, 4, 1, 4, 7. The mode is 4 because that number appears twice while all other numbers appear once. How about the mode of this dataset? 0, 0, 1, 1, 2, 7. This dataset has two modes, 0 and 1. These two values appear equally often and more often than any other data values. Note the difference between mean and median on the one hand and mode on the other hand. A numerical dataset has exactly one mean and exactly one median, whereas a dataset may have more than one mode. Now, having multiple modes is not necessarily difficult to interpret. Consider, for example, figure 4.13, which shows that the modal days for doing laundry are Wednesday and Sunday. Now, these are fake data that I made up for this illustration, but the interpretation is simple. People are most likely to wash their clothes on Wednesdays and Sundays. On the other hand, it makes no sense to compute the mean of this data set. The average laundry day is not Thursday and a half. Graphically, the mode is the bar with the tallest peak in the bar plot. So figure 4.13 shows made-up data showing preferences for when to wash clothes. There are 7 bars in the bar plot, labeled Monday, Tuesday, Wednesday, and so on through Sunday. The y-axis shows counts from 0 up to 14. And what we see in this graph is that Wednesday and Sunday have the highest counts, and there is a horizontal dashed line to indicate the most common value, which is the mode. Now, because these data are circular, you could visualize them using a polar plot, although I think the mode is easier to see in a linear plot. But try it and see if you disagree with me. Section 4.4, Measures of Dispersion. Dispersion refers to the width of a distribution. Imagine creating a distribution of the salaries of 1,000 people who all have the same position in the same sector, for example, all managers at a certain restaurant chain, versus a distribution of the salaries of 1,000 people randomly sampled from any position in any industry. This is depicted in figure 4.14, which I will explain in a moment. The restaurant manager's salaries won't all be identical, but they will be reasonably close to each other. The salaries of randomly sampled people, however, will include salaries at the lower end of the wage scale and at the higher end of the wage scale. Figure 4.14 shows made-up data illustrating the concept of dispersion. There are 4 panels, 2 panels on top, 2 panels underneath. The left top panel, panel A, is titled Restaurant Manager Salaries. It shows a scatter plot of a lot of data that are all clustered around the value of around 70. There are 1,000 values, and it looks like the range is from around 65 to 75, so fairly tightly clustered around the value of 70, which corresponds to thousands of dollars in terms of salary. To the right of that is panel B that shows another scatter plot with the same X and Y axis limits, but the variability is much higher. So you have a lot of data points around 40 and data points up to 100. Below panel A, so bottom left, we see 2 box plots. One box plot for the restaurants and one box plot for the random samples from a variety of industries. And you can see that the clustering of the restaurant salaries on the left is much, much smaller. So the data values are much more limited compared to the random sampling of various salaries on the right, which has a much more elongated, vertically elongated box plot. Finally, we have panel D on the lower right that shows histograms depicted as lines of the salaries for the two different industries. So restaurants, that is a tightly clustered histogram. It has a very narrow Gaussian with a sharp peak versus the random line, which is much more broad and it has a lower peak because it is more distributed. Back to the text. I've created these two data sets to have the same mean, but different dispersions. There are different ways to quantify the dispersion of a data set that I will describe in this section, but I hope that the figure I just described illustrates the concept. Section 4.4.1 Variance. The notation for population variance is sigma squared, and the notation for sample variance is S squared. You might sometimes see sigma squared sub x, so x in the subscript, or var x, so in italics, var, and then in parentheses x, to indicate the variance of data variable x. Equation 4.5 shows the formula for variance. Equation 4.5 is s squared on the left-hand side, and the right-hand side is 1 over n minus 1 times the sum from I equals 1 to n of the quantity x sub I minus x bar, that quantity squared. There is a margin note that reads, mu and sigma are for populations, x bar and s are for samples. But that notation is not universally adopted, so be mindful of the context. You might also see sigma caret, so sigma with a caret or an umlaut symbol on top, for sample standard deviation to convey the idea that the sample standard deviation is an estimate of the population standard deviation. Back to the text. In other words, to calculate variance, subtract the data average from each individual data value, square that difference, add all of these squared differences, and divide by 1 minus the sample size. In other words, the average of the squared deviations from the mean. I'm sure you have several questions about that formula, and I will answer them in a moment. But first, I want to show a few examples. Use equation 4.5, that's the equation for variance, to compute the sample variance of the following dataset. Dataset P equals 8, 0, 4, 1, minus 2, 7. Did you get the answer? It's 16. The average is 3. Let's try another example. Dataset Q equals 2, 3, 4, 3, 4, 4. The variance of Q is 2/3. What do those two values signify, and how do you interpret the fact that the variance of P is 24 times greater than the variance of Q? I believe that a visual representation of these data sets will be helpful. This is illustrated in Figure 415. Figure 415 depicts two panels, one on top of the other. Both show the real number line going from around minus 10 to plus 12, with circles, white circles, indicating the locations of the data points for dataset P and dataset Q on the real number line. And what you see is that dataset P has the circles more widely distributed across the number line. Dataset Q has multiple data points that overlap on the real number line. Back to the text. You can see that data P are more dispersed than our data Q. Does it look 24 times as dispersed? Perhaps not, but variance involves squaring numbers, and squared numbers can grow really large. Variance is appropriate for any numerical or ordinal data set. Now, you might think that it would only be interpretable for distributions where the mean is easily interpretable because the mean is in the variance formula. Indeed, variance reflects the spread of the data around the mean. But variance is an insightful measure even if the data distribution is not unimodal or symmetric, especially when comparing variances across different data sets, as long as they have similar distribution shapes. Below, I will pose and then answer several questions about the variance formula. When you read each question, I encourage you to think of an answer before reading my text or listening to the explanation. It doesn't matter if you get the same answer as I do. The important skill is to look at a mathematical formula and think about it critically. The equation is reproduced below for convenience. I will repeat it. Again, it is s squared equals 1 divided by n minus 1 times the sum from I equals 1 to n of the quantity xi minus x bar squared. Question: why mean center? The reason to mean center is that we want the variance to reflect the dispersion within the dataset, regardless of the distance of the dataset from zero. For example, mean centering ensures that the following two datasets have exactly the same variance. Dataset D1 is 1, 2, 3, 3, 2, 1. Dataset 2 is 101, 102, 103, 103, 102, 101. In other words, dataset D2 is exactly the same as dataset D1, except 100 has been added to each element. Question: why are the differences squared? The differences between each data value and the mean are squared to give a measure of distance from the mean. Consider what would happen if you tried to apply the variance formula to dataset D1 without the squaring. You would get a result of 0. So without squaring, the quote-unquote variance equals 0. That's not a quirk of this specific example. It is tautologically the case that any mean-centered dataset sums to 0. But why do we need to square the differences? Couldn't we take the absolute value instead? The answer is yes, we could. That's a different measure. It's called mean absolute difference, and its formula is below in equation 4.8. Mean absolute difference is often abbreviated MAD or MAD. It equals 1 divided by n minus 1 times the sum from I equals 1 to n of the absolute value xi minus x bar. Why is variance used more often than mean absolute difference? Turns out that variance has several nice mathematical and statistical properties that make it advantageous over the mean absolute difference, including, number 1, variance emphasizes larger values, which facilitates detecting outliers and is used in applications including assessing financial risk. 2, variance is continuous and has a cleaner derivative, which is useful for optimization. 3, variance is closely related to Euclidean distance and therefore has a nice geometric interpretation. 4, variance is the second quote-unquote moment of a distribution. More on statistical moments later in this chapter. 5, variance is closely related to the all-important least squares algorithm for fitting regression models to data. To be fair, mean absolute difference is also a useful measure of dispersion and is less strongly influenced by outliers or extreme values in the data. It is used in some machine learning and optimization methods, but variance is far more commonly used in statistics as a measure of data dispersion. Question: why divide by n minus 1? This is a tricky question and a common source of confusion. For starters, it should be obvious that you want to scale down the measure of variance by sample size. Otherwise, the variance will trivially increase with more data, even if the amount of dispersion is the same. In other words, scaling by sample size gives us an average dispersion instead of the summed dispersion. But why divide by n minus 1 instead of n? Well, it turns out that dividing by n minus 1 is for sample variance, s squared. If you have access to the entire population, you would divide by n to obtain sigma squared. There are several explanations for this. I will provide one, and I hope it makes sense. Consider a six-sided die. Die is the singular of dice, not the same word as death. The expected average value of all 6 faces of a die is 3.5. This is the average of 1, 2, 3, 4, 5, 6. Now, I write expected average because the empirical average from a finite number of die rolls is unlikely to be exactly 3.5. Imagine that you roll the die 4 times and the sample mean is 3. Now, here's a question. Given that you know that the mean is 3, how many of those 4 die rolls do you need to know the value of? All 4? What if I told you that 3 of those rolls landed on 1, 2, and 4? Based on knowing that the average is 3, you don't need to observe the 4th roll. You can compute it to be 5. It must be 5. It cannot be any other value. This means that once you know the average value of a sample, there are n-1 unique values that the data can take on. The final data value is entirely determined. Thus, n-1 is the degrees of freedom for this statistic. Degrees of freedom is a concept that I will discuss more in Chapter 10. For now, suffice it to say that it is the number of data values that can independently vary. So, once you know the sample mean, there are n-1 possible unique values that the data can take, and this becomes the normalization to scale down the summed variance. We divide the mean by n because there are no entirely determined data values before knowing its mean. An implication of this division is that variance is undefined for a dataset with only one value, that is when n equals 1, although the average of an n equals 1 dataset is defined. Section 4.4.2, Standard Deviation. Mathematically, the take-home of this section is simple. Standard deviation is the principal square root of variance. In other words, if the variance is s squared, then the standard deviation is s. It is also sometimes indicated as stdx or just std. Footnote. Yes, I am aware it's the same abbreviation as sexually transmitted diseases. Every university freshman makes jokes about it, which I encourage. After all, both STDs are too serious not to joke about. Back to the text. Equation 4.9 shows the formula for standard deviation. We have s on the left-hand side equals the square root of 1 divided by n-1 times the sum over xi minus x bar squared. In other words, it is simply the square root of the variance. Why do we have a standard deviation when it's the same thing as the square root of variance? Or, why do we have variance when it's the same thing as standard deviation squared? These two quantities are, of course, closely related, both mathematically and conceptually. They both reflect the spread of the data around the mean. Standard deviation is often easier to interpret because it has the same units as the data, whereas variance has those units squared. For example, the standard deviation of height data is feet, whereas the variance of height data is feet squared, which is a little less intuitive to conceptualize. Now, there are statistical procedures where either variance or standard deviation is used. You will learn about those as they come up during the book and elsewhere in your adventures through statistics. For example, one of the most common data normalizations is called z-scoring and involves transforming the data into units of standard deviation. Results from statistical analyses such as regression can be normalized to standard deviation units to facilitate interpretation and comparison. The main thing to keep in mind for now is that standard deviation and variance are related to each other through a square, and that sometimes one or the other is preferred for interpretational or mathematical reasons. Section 4.4.3, Heteroscedasticity and Homoscedasticity. First of all, heteroscedasticity is a really fun word to say. I encourage you to say it out loud, as I just did, and challenge your friends to say it as fast as possible after a few alcoholic drinks. Footnote: I asked ChatGPT to generate some tongue twisters. Here's my favorite. Heteroskedasticity habitually hobbles homogeneous hypothesis heuristics, harrowing statisticians. End footnote. Homoskedasticity characterizes a variable that has equal variance at all values. The opposite of homoskedasticity is heteroskedasticity, which is the idea that the variance of a variable changes as a function of the value of that variable. Figure 4.16 shows an example in which the variance does and does not increase with the x-axis. Figure 4.16 has two panels, panel A on the left, titled Homoskedasticity, and panel B on the right, titled Heteroskedasticity. Both panels show scatter plots with data index on the x-axis and data value on the y-axis. In panel A, we see that the dispersion of the data is the same across the entire x-axis, whereas in panel B, we see that the dispersion of the data increases with the x-axis. In other words, the data towards the left of the distribution are very tightly clustered around one center value on the y-axis, and the further we get to the right, so the increase in the data index, the larger the dispersion or the distance across the y-axis that the data take up. Back to the text. Slightly less fun, but equally descriptive, terms that describe these concepts is homogeneity of variance and heterogeneity of variance. Heteroskedasticity is relevant for several analyses, including correlation and regression. When heteroskedasticity is present, correlation coefficients are less interpretable, standard errors of coefficients can be inflated, and significance tests can become unreliable. A real-world example of heteroskedasticity is wealth and expenditures. As wealth increases, so does the variability of consumption expenditures. Low-income households have similar levels of expenditures because there's a lower limit to how much they can spend, basic needs like food, rent, and so on, and they are limited in large purchases. In contrast, high-wealth households have more disposable income and therefore purchase both low-cost items and also high-cost items like expensive electronics, appliances, cars, vacations, and so on. Section 4.4.4, Full width at half maximum, FWHW. Full width at half maximum is a measure of the width of a Gaussian function. It can be computed analytically or empirically, and it is interpretable for any roughly Gaussian-shaped distribution. Full width at half maximum is quite a mouthful. What does that phrase mean? Well, imagine a Gaussian function, like a bell curve, that is normalized to have a peak of 1 or 100%, and that tapers to 0 on both sides. This means that there will be data values on either side of the peak that equal 0.5 or 50%. This is the half maximum. And the distance on the x-axis between these two half maximum points is the FWHM, full width at half maximum. Figure 4.17 illustrates the idea. Figure 4.17 depicts a Gaussian function, so a bell curve function, with 0 at the center, and the x-axis goes from -8 up to +8. The y-axis is labeled gain, and has tick marks at 0, 50%, and 100%, which corresponds to the peak of the Gaussian. And then we see that the 2 points of the Gaussian function that cross the 50% gain horizontal axis are indicated with a horizontal arrow, and there are vertical dashed lines that go down onto the x-axis. They intersect the x-axis at roughly -2.1 and +2.1. And the arrow, the horizontal arrow, is indicating that the full width at half maximum is the distance between the two x-axis points where the Gaussian function is at 50%. So from minus 2.1 to plus 2.1, full width at half maximum would be somewhere around 4.2. Back to the text. The full width at half maximum can be calculated analytically for a Gaussian function. So there are two equations here. Equation 4.10 shows g of x on the left-hand side. The right-hand side is the natural exponential, so e to the quantity minus x squared over 2 sigma squared. And then equation 4.11 is the full width at half maximum of g of x equals 2 times sigma times the square root of 2 times the natural log of 2. There's a margin note that reads, the sigma in this context does not indicate population standard deviation, although this parameter is conceptually comparable to variance in that it encodes the width of the Gaussian function. Back to the text. On the other hand, full width at half maximum is not directly computable for an empirical distribution. In this case, you can apply an algorithm to compute the full width at half maximum from an empirical data distribution. I will explain the algorithm in exercise 10. If you're up for a challenge, you can try to develop your own algorithm before reading those instructions. Section 4.4.5, Fano factor and CV. I mentioned earlier in this chapter that the interpretability of the mean, even for a symmetric unimodal distribution, depends in part on the variance. The smaller the variance, the more the data values are clustered around the mean. This is the case for a roughly normal distribution. The idea of the Fano factor and coefficient of variation, which is abbreviated CV, is to capture this interaction. The formulas are similar. Here we have the formula for Fano factor indicated as FF equals S squared divided by X bar. And the formula for CV, coefficient of variation, equals S divided by X bar. There's a margin note that reads, the notation sigma divided by mu is used when describing a population or a theoretical characteristic. Back to the text. These quantities are sensible only for datasets that have positive means and are usually applied to datasets that have strictly positive values. You can imagine why that's the case by looking at the denominator in the equation. A dataset with values equally distributed around 0 has a mean of or close to 0, which means that the Fano factor or the coefficient of variation could be undefined, could blow up towards infinity, or could be negative, all of which are uninterpretable results. The interpretation of these metrics is that as they tend towards 0, there is little variance compared to the mean, and as they increase, the dispersion becomes much larger than the mean. This means that the Fano factor and CV can be used as measures of inverted signal-to-noise ratio. Fano factor and CV are used in computational scientific fields such as biology, physics, and neuroscience. This paragraph refers to figure 4.18, which depicts 3 different roughly Gaussian distributions with Fano factors of 0.1, 1, and 10. So the Fano factor, the distribution with a Fano factor of 0.1 is extremely narrow, it's very peaky, and the distribution with the Fano factor of 10 is much wider, and the Fano factor with the distribution with a Fano factor of 1 is in between those two extremes. Back to the text. The primary difference between the Fano factor using variance and CV using standard deviation is the units. Fano factor retains the units of the data, while the CV is a unitless ratio. You can work this out in an example. You measure the durations that a computer takes to implement an algorithm. The Fano factor will have units of milliseconds squared divided by milliseconds, which is milliseconds, whereas the CV will have units of milliseconds divided by milliseconds equals 1. Section 4.5, Interquartile range often abbreviated IQR. IQR is another measure of the spread of a dataset, and I introduced it briefly in section 3.5 on box plots. IQR is the numerical distance between 25% and 75% of the data. In particular, IQR is computed using the following steps. This is visualized in figure 420, which I will describe after defining these steps. Step 1, compute the median of the data. Let's call this median quartile 2 or Q2. Step 2, compute the median of the subset of data that is less than Q2. So this is the data that are left of the median in a histogram. And we'll call that quartile 1 or Q1. Step 3 is to compute the median of the subset of the data that is larger than Q2. And we will call this quartile 3. And step 4 is to subtract Q1 from Q3, and that is the inner quartile range. Figure 420 visualizes the interquartile range. There is a histogram which shows a distribution of some random data. There are 3 downward-facing arrows in the histogram that indicate the 3 quartiles. So we have Q1, Q2, and Q3. 50% of the data are between Q1 and Q3. 25% of the data are left of Q1. 25% of the data are right of Q3. And the interquartile range is defined as the distance between Q1 and Q3. Parenthetical note, as an aside, I find the labels quartile 1 through 3 unintuitive because the quartiles are the data regions while the median values are their boundaries. Indeed, the 4 quadrants have 5 boundaries. I would prefer terms like P25 and P50 and P75 where the P indicates percentile. But once terminological conventions are set, they are nearly impossible to change. A rose by any other name. End parenthetical note. The interpretation of IQR is that a relatively smaller IQR indicates a tighter distribution, whereas a relatively larger IQR indicates a more spread out distribution. IQR retains the units of the data, which facilitates interpretation within a dataset, but can impede direct comparisons across datasets unless they're in the same units. IQR is a non-parametric measure of variability because it's based on medians instead of means. And for this reason, IQR is insensitive to outliers. Section 4.6, QQ plots. The best part of QQ plots is their name. It's just fun to say out loud. Everything else about QQ plots is, well, let's just say that QQ plots take a bit of experience to get comfortable with. The first Q stands for quantile, where quantile is the general term for cutting the data into equal-sized bins. For example, IQR involves binning the data into 4 quantiles. The second Q also stands for quantile, so QQ plot is short for quantile plot. A QQ plot shows the relationship between an empirical data distribution and a theoretical Gaussian distribution. The purpose of a QQ plot is to qualitatively assess whether a given distribution looks like a Gaussian distribution. QQ plots are therefore used to determine whether data are appropriate for statistical procedures like ANOVA and regression and to detect problems with a dataset. As an introduction to QQ plots, let's imagine that I gave you 2 datasets and asked you to determine whether those data were sampled from a population with a Gaussian distribution. How would you go about this determination? Well, of course, you would plot histograms of the data. Now, if this wasn't your idea, then it's okay to pretend that it was. And to help you determine the Gaussianness of the distributions, you might plot a normalized analytical Gaussian on top of each histogram. You can see in figure 421 that the histogram in panel A looks a lot like an analytical Gaussian, whereas the histogram in panel B does not, notice that the probability values of the histogram in panel B drop precipitously on the left side instead of smoothly tapering down, and that the right tail appears larger than that of a Gaussian. Figure 421 has 4 quadrants, 4 panels. For now, I will just talk about the top row, so panel A and panel B. These show 2 histograms for different random data distributions. The histograms are depicted as black lines, and the gray dashed lines are analytic Gaussian distributions that are drawn on top. In panel A, we have data drawn from a Gaussian distribution, so the analytical Gaussian closely matches the empirical histogram. In panel B, however, the empirical distribution looks kind of like a power law distribution, so there are many values with data values close to 0 and relatively fewer data points with larger values. Now, the distribution does not look like a histogram, so the analytical Gaussian does not match the empirical distribution. Back to the text. The idea of a QQ plot is to provide a visual representation that more effectively shows the comparison between an observed distribution and a theoretical Gaussian distribution. In particular, each panel in figure 421A and B has 2 lines, one for the empirical histogram and one for the analytical distribution. The QQ plot combines these lines, which I have just described to you, into one graph. So the x-axis on a QQ plot is the analytical Gaussian, and the y-axis is the empirical data. Now consider that if the data were sampled from a purely Gaussian process, then all of the data points would lie on the diagonal. In contrast, the less Gaussian distributed the data, the less the data will fall on the diagonal of the QQ plot. So with that in mind, consider the left-hand column of figure 421. These data were created by sampling from a normal distribution. So of course, we expect the data points to be on the line in the QQ plot. This is depicted in figure 421C, which I will describe in a moment. Due to sampling variability and maybe some noise, the sampled data points are not all exactly on the diagonal, but they are pretty close. So panel C of figure 421 shows a scatter plot with black dots and a dark gray line indicating unity between the x-axis and the y-axis. And what you see is that the black dots correspond to the values of the data, the empirical data, and they lie more or less along the diagonal with some exceptions, particularly as you get further out towards the extreme values, but mostly the black dots are on the diagonal line. In other words, the dots are consistent between the theoretical quantiles from a pure Gaussian and the data values from the actual empirical data. Back to the text. Now consider the right-hand column of figure 421. These data were drawn from a power distribution, which definitely does not conform to a Gaussian. So the first thing to notice in the QQ plot in panel D, which I will describe in a moment, is that the data do not fall on a diagonal line. And the deviations off the line do not simply look like non-systematic noise due to randomness and sampling variability. Instead, there is clearly something systematic in the data that makes it look different from what you would expect for a normal distribution. In other words, the data are not normal. Margin note. In distributions, the opposite of normal is not abnormal. There's nothing wrong with non-normal distributions, but knowing the shape of the distribution will help you understand the data and determine the appropriate statistical procedures to apply. So panel D of figure 421 shows a QQ plot. Again, it's a scatter plot similar to panel C, which I have previously described. However, the data clearly do not lie along the line of unity. In particular, the scatter plot looks a little bit like a smile or like a U-shaped, where the data points are systematically above what would be expected for a theoretical Gaussian for values less than around 1.7, and for for values greater than somewhere around 1.9 or 2. Furthermore, the empirical data values are below the line, so less than what would be expected for Gaussian for data in the range of around minus 0.5 to 1.8. Back to the text. Now for the tricky part. How exactly to interpret the deviations from normal? One way to interpret the QQ plot is to compare specific numerical values on the x and y axes, for example, the number 3. So a vertical line that passes through x equals 3 in panel D of figure 421 crosses the data at around y equals 6. This means that the data are stretched to the right, meaning larger data values than what you would expect for a normal distribution. Now consider a vertical line that passes through x equals minus 3. This touches the empirical data at around y equals 0. The interpretation is similar. The empirical data values are larger, in other words, shifted to the right, than would be expected given a normal distribution. In fact, the empirical data never go lower than 0. The data have no values below the center of a normal distribution. I hope that description makes sense. As I wrote at the outset of this section, QQ plots take a little bit of practice to get used to. That said, you typically don't need to go too deep into the precise interpretations of the different regions of QQ plots. Mostly, we are just interested in determining whether the empirical distribution follows roughly the Gaussian, which would be evidence for normal distribution, or not, which would be evidence for a non-normal distribution. Understanding the mechanisms of creating a QQ plot relies on understanding probability functions, and you'll learn more about that in Chapter 8. For now, focus on the idea that a QQ plot shows how the data on the y-axis relate to a theoretical normal distribution on the x-axis. I will provide a more detailed description of how QQ plots are created later in the book. Final statement for this section: you can make a QQ plot using any analytical distribution on the x-axis. Most of the time, the normal distribution is used, but that's because of its importance in statistics and not because of any constraint on how QQ plots are constructed. Section 4.7, Statistical Moments. Statistical moments are numbers that describe the shape of a distribution. Each distribution has a first moment, a second moment, and so on. In practice, the first two moments are the most commonly used, and it is rare to report more than the fourth moment. In fact, you already know the first and second moments. You've been calling them mean and variance. So I think you will find that generalizing these characteristics to moments is intuitive and eye-opening. Section 4.7.1, Unstandardized and Standardized Moments. I have organized this section into subsections for each of the first 4 moments, but before discussing details and interpretations of these specific moments, I want to show you 2 formulas and a table that provides a top-level overview. Let's start with the general formula for the unstandardized moments. The kth moment of a distribution for dataset X is defined as equation 4.14, which states that m sub k, so moment sub k, equals 1 divided by n times the sum from I equals 1 to n of the quantity x sub I minus x bar 2. So that difference to the kth power, where n is the sample size and I indexes each of the n elements in the dataset. You can see that all statistical moments are defined from the same formula raised to higher powers before summing. I will discuss the significance of this in the following subsections. Now, the division by n ensures that larger datasets will not trivially have larger values of m. However, data scaling will lead to different values of m. For example, the same dataset measured in millimeters versus meters will have a very different value of m sub k. For this reason, the numerical values of the unstandardized moments can be difficult to interpret and impossible to compare across data sets with different numerical scales. Therefore, it is common to normalize the moments by the standard deviation raised to the kth power, and this normalization removes the scale from the data. So, here we have equation 4.15, which states that m sub k equals 1 divided by the quantity n times sigma to the power of k, where sigma is the standard deviation. This assumes that the standard deviation is known. Of course, in practice, you estimate sigma using S, the sample standard deviation. So 1 over n times sigma to the power k times the sum from I equals 1 to n of the quantity xi minus x bar to the power of k. Figure 422 provides an overview of the first four moments, their statistical terms, and their formulas. And you can refer back to this table as you listen to or read the rest of this section. Figure 4.22 shows a table that contains 4 rows for the first 4 moment numbers, so the first, second, third, and fourth moment. And then we have columns corresponding to the moment number, so 1 through 4, the name, the description, and the formula. So the names are mean, variance, skew, and kurtosis for the first 4 moments. The description is average for the first moment, which is the mean. The second moment is the variance that describes the dispersion. The third moment is called skew that describes the asymmetry. And the fourth moment is the kurtosis, and that describes the tail fatness. Back to the text. Section 4.7.2, first moment, mean. The first moment of a distribution is the mean, the average value. That comes from setting k equals 1 in equation 4.14. Now, setting k equals 1 actually means that m1 equals 0. That's trivial, regardless of the mean of the data. Thus, formally, the first moment of every distribution is 0. So therefore, in practice, the mean centering term is dropped, and the first moment is defined as equation 416, which states m sub 1 equals 1 divided by n times the sum from I equals 1 to n of x sub I. Of course, you recognize this formula as the formula for the mean. This is sometimes called the raw first moment. And you also know that the interpretation of the first moment is the central tendency of the distribution. It's the center of mass of the data, like the fulcrum point upon which the histogram is balanced. Section 4.7.3, second moment, variance. You already know the second moment of a distribution. It's the variance, or the spread of the data around its mean. Compare equation 415 with k equals 2 to equation 4.5, which I referenced on page 101. Now, when you see that the second moment is the same as variance, you will also see that the standardized second moment is trivially equal to 1. It's the variance divided by the variance. So therefore, the unstandardized second moment is used in practice. Section 4.7.3, third moment, skew. All right, now we are getting to new material. The third statistical moment is called skew, and the amount of skew in a distribution is called its skewness. Skew is related to the asymmetry of the variance around the mean. The third moment is typically computed using the standardized formula. This does not trivially take on a specific numerical value for all data sets. The skewness of a pure Gaussian is 0, which should make sense considering that Gaussians are perfectly symmetric. A distribution that is pulled to the left of the mean in a histogram is said to have a negative skew or a left skew, and a distribution that is pulled to the right of the mean of a histogram is said to have a positive skew or a right skew. This paragraph references figure 423. Figure 423 shows an illustration of skewed distributions. We have two panels. Panel A illustrates a left or a negative skew on top, and panel B on the bottom illustrates a right skew or a positive skew. So the top panel with the left or negative skew shows a distribution that looks kind of like a Gaussian, but the left tail is really pulled to the right. So there's a lot of more data values to the left of the peak of the distribution. And in the lower panel with the right or the positive skew, we have the opposite. So we have a distribution that sort of looks like a Gaussian, but there are many data values that are pinched off to the right of the peak. Inside the panels, we also see a simplified equation. On the top with the left skew, we have the sum of x minus x bar cubed is less than 0, so negative skew. And on the bottom, we see that the sum of the quantity x minus x bar cubed is positive or greater than 0. Back to the text. Why does the third moment reflect the lopsidedness of a distribution? Consider that mean centering produces negative numbers for values left of the mean and positive numbers for values right of the mean. Now, raising numbers to an even power gives non-negative results. For example, minus 2 squared is 4, just like 2 squared is 4. But raising numbers to an odd power preserves the sign. So minus 2 cubed equals minus 8, but plus 2 cubed equals plus 8. Therefore, if there are more extreme numbers left of the mean compared to right of the mean, the average of all of the mean-centered cubed data values will be negative. Hence, skew is driven by left-right asymmetries of the distribution around the mean. Section 4.7.5, Fourth moment, kurtosis. The fourth moment is called kurtosis, and the standardized version is most often computed and reported. Before reading the text below, try to infer the interpretation of kurtosis based on the distributions in figure 4.24. Now, all three of the distributions in that figure have the same mean, but the tails of one fall to 0 faster than the tails of the other. This is what kurtosis measures. So figure 424 illustrates three distributions, so three histograms, all plotted on top of each other using lines. There is a solid dark gray line that illustrates no excess kurtosis. It looks like a Gaussian distribution. And then we have a black dashed line that is called negative kurtosis, and that is wider, so it trails off to 0 on both sides of x equals 0. It goes down to y equals 0 more slowly, so more gradually than what you see in the solid gray line with no excess kurtosis. And then we have a light gray dotted line that is indicating positive kurtosis, and that falls to 0 quickly. So the distribution is much tighter. It's much narrower than the other two distributions. Back to the text. The interpretation of kurtosis is the fatness of the tails. The question to ask with kurtosis is whether the distribution falls to 0 faster or slower compared to a pure Gaussian. So the kurtosis of a pure Gaussian is 3, and therefore it is common to report kurtosis as the measured kurtosis minus 3. This is called excess kurtosis. Positive kurtosis, or if unshifted, kurtosis greater than 0, means that the distribution tails fall to 0 more sharply than a Gaussian. That is, the tails are thin. Whereas negative kurtosis, or if unshifted, kurtosis less than 3, means that the distribution tails fall to 0 more gradually than a Gaussian. That is, the tails are fat. Here we have a footnote. Footnote 10. Negative and positive kurtosis are also called platykurtic and leptokurtic, respectively, but I don't recommend memorizing those terms. They sound more like dinosaur names than statistical terms to me. Back to the text. From inspecting equation 414, you might be tempted to think that kurtosis is simply the squared variance. That is not the case because the power k is inside the summation, not outside. It's the same reason why variance is not simply the mean squared. In fact, kurtosis and variance are independent descriptions of a dataset, and it is possible to manipulate one without the other. You can see an example of this in figure 425, which you can explore more in the online code and also in exercise 7. So figure 425 illustrates 3 distributions with identical means and variances, very similar skews, and yet very different kurtoses. So we have 3 distributions. One is a really, really narrow peak. That is distribution D1. That has a kurtosis of around 0.1, excess kurtosis of 0.1. And then we have a distribution that looks kind of like a uniform distribution. That is distribution D2. It has a kurtosis of minus 1.1. And then we have kurtosis or distribution D3, which kind of looks like a Gaussian. It's a bit noisy. These are empirical sample data. And the kurtosis or the excess kurtosis of distribution D3 is around 0. Now, the figure also depicts a table of the mean, the variance, the skew, and the kurtosis. So far I've described that the kurtoses of these 3 distributions are very different from each other, whereas the mean is exactly 0 in all cases, the variance is exactly 1 in all cases, and the skew is roughly 0 in all 3 distributions. Back to the text. Kurtosis is highly sensitive to outliers because deviations from the mean are raised to the 4th power. So this makes kurtosis a useful measure of extreme events in a data set. For example, kurtosis is used to assess risk in financial data, and it is used to isolate signals from noise in multivariable data sets through a technique called independent components analysis. Section 4.7.6, What to Memorize. There are many interesting details of statistical moments that could be explored, but there is so much to learn about applied statistics and so little time. Figure 4.26 shows my advice for what to commit to memory about the statistical moments. So figure 426 shows a table of things to memorize. So it has 4 rows and 4 columns. It is actually very similar to a table I described earlier. So reading the rows across, we have the first moment is called the mean, and the interpretation is that it's the average of the data. The second moment is the variance, and it describes the dispersion of the data. The third moment is called skew, and it describes the asymmetry of the data. And the fourth moment is kurtosis, and it describes the tail fatness of the data. The final column of each of these rows depicts a simplified picture that shows a Gaussian or a series of Gaussian distributions depicting the feature to memorize. Section 4.8, Histograms Part 2, Number of Bins. Now that you have gained some experience creating and working with histograms, it is time to return to the issue of the number of bins to use when creating histograms. By the way, this is the same issue as the width of the bins because the number of bins determines their widths and vice versa. Previously, I have written qualitatively that too few or too many bins is not useful for interpretation. In this section, I will introduce you to several guidelines for computing the number of bins in a histogram. Now, these are sometimes called rules, but scientists are not the type to blindly trust authority figures, so we consider them to be mere suggestions. I will start by defining the relationship between bin count, that's variable k in equation 417, and bin width, that is variable w in equation 417. So equation 417 defines K, which is the number of bins, to be equal to the ceiling of the ratio of the maximum of X minus the minimum of X divided by W. So X is the data. So we have the range of the data. So max of X minus the min of X divided by the bin width, which is variable W. And you take that ratio that's unlikely to be an integer. So then you take the ceiling of that ratio, and that is the parameter K, which is the bin count. Back to the text. There are several ways to determine the number of bins. I will focus on 3 common methods. They are presented in figure 427 and are expanded in the following text. So figure 427 shows a table that provides an overview of histogram bin guidelines. So we have 3 rows and 3 columns. The first row is the arbitrary method. There, the formula is you set K to be 40, for example. The key advantage in the third column is that it is simple. And then the second column, or the second row, is the Sturgis method. And here the formula is K equals log base 2 of n plus 1. And the key advantage is that it depends on the count, so the number of data values. And then the third row is the Friedman-Diaconis method. Here the formula defines W as 2 times the ratio of IQR to the cube root of n. And the key advantage is that it depends on both the count of the data and the spread of the data. Back to the text. The quote-unquote arbitrary guideline is simply to define the number of bins to be 40 or any other number. This is simple, straightforward, and easy to reproduce. It works well for many data sets with sample sizes of hundreds or larger. The Sturgis and Friedman-Diaconis rules, and Friedman-Diaconis is often abbreviated FD. These guidelines provide bins that adapt to the data. Many people consider the FD rule to be the best because it adapts both to the sample size and to the variability of the data. Note that the arbitrary and Sturgis rules involve specifying K, the number of bins, whereas the FD rule involves specifying W, from which you compute K. Now, in practice, you don't need to implement these methods yourself. Python and R will do the calculations for you when you specify the bin's input parameter. Now, these guidelines that I've presented so far specify the same widths for all bins. In principle, it's possible to vary the bin width as a function of the data. However, that is not a good idea. Variable width bins look neat, but are more difficult to interpret and to compare between data sets. This paragraph references figure 428, which shows a histogram in which each bin in the histogram, so each bar of the histogram, has a different width. And the figure caption reads, "Variable bin widths make cool looking graphs, but use it on a t-shirt, not in official data presentations." Section 4.8.1, Other Descriptive Stats. By no means does this chapter provide an exhaustive list of all descriptive statistics. Biological and physical observations can be characterized by distributional characteristics like the Hurst exponent, time series data of characteristics like spectrum and autocorrelation. Multivariate data sets contain covariance matrices, and data matrices can be described by quantities like rank, condition number, singular value spectrum, and so on. Descriptive statistics not introduced in this chapter tend to be more specific to a particular discipline. The good news is that the less commonly used descriptive statistics are based on the concepts and procedures that you learned in this chapter. Section 4.9, Exercises. I am not going to read these exercises or discuss their solutions here in this audiobook because I discuss them on my YouTube channel in a series of videos specifically about these exercises. End of chapter 4.